Thank you for standing by. Today's call will begin momentarily. If you'd like to ask a question on today's call, please press star 1 and record your name. Again, today's call will begin momentarily. Thank you.
Good morning, and thank you for joining us today for this media teleconference providing a project update for the X-57 Maxwell. I'm Rob Margetta with NASA's Office of Communications. I'd like to introduce our speakers now and then turn this over to them. After their remarks, we'll take questions. Today, we'll be hearing from Bradley Flick, the Director of NASA's Armstrong Flight Research Center, Kate McMurtry, Deputy Director for the Integrated Aviation Systems Program within NASA's Aeronautics Research Mission Directorate, Vince Schultz, X-57 Deputy Project Manager, and Sean Clarke, X-57 Principal Investigator. And with that, I will turn this over to Brad for his remarks. Thank you.
Thanks. I'll start with a little bit of background on the project just to get us all calibrated, and then talk a little bit about why we're here, then we'll continue through the program. So in 2014, NASA's Aeronautics Research Mission Directorate made an investment in the fledgling electrified propulsion technology areas with the testing of a truck-mounted high-lift wing with distributed electrically powered propellers. We called that the Leap Tech project out here at Edwards Air Force Base, working with two small companies, Empirical Systems Aerospace, or ES Aero, and Joby Aviation. That was an interesting test, and it planted a seed that grew into the development of a flight research project, ultimately known as the X-57 Maxwell. The project was formulated as a multi-phase effort, starting with the electrification of a Tecnam P-2006 aircraft and culminating with the flight of a high-lift wing with distributed propulsors for takeoff and wingtip-mounted electric motors for cruise. It was a bold plan based on the belief that component technologies were commercially viable and available to be integrated into a flight vehicle. I'll let Vince and Sean and the project team discuss the specific challenges encountered and the technology developments made along the way. But what we learned is that many of those necessary subsystems were not sufficiently mature for safe flight. So in 2021, NASA adjusted the project objectives, recognizing that the technical lessons being learned in the electrification of the aircraft were ultimately more critical to the advancement of the industry than was the demonstration of the high-lift technology that we originally set out to do. At that time, we decided to fund the team through the end of this fiscal year, FY23, to advance the technology as far as they could and publicly share the knowledge gained. We anticipated at the time that would be sufficient to achieve flight of the electrified vehicle. Unfortunately, we recently discovered a potential failure mode in the propulsion system that we've determined to pose an unacceptable risk to the pilot safety and the safety of personnel on the ground during ground tests. Mitigation of that failure would take the project well beyond its planned end at the end of this fiscal year. So NASA has decided to end the project on time without taking the vehicle to flight. So while we're not achieving those original project objectives or realizing the full value of taking the system to flight, the knowledge gained from the development of the X-57 has elevated the state of the industry and has informed standards for current and future electrified aircraft. NASA is proud of this team, and we will celebrate their accomplishments. Like I said earlier, the project members will do a much better job than me talking about those specific accomplishments, and their turn is coming up. So at this time, I'm going to turn the microphone over to Kate McMurtry, the Deputy Director of NASA's Integrated Aviation Systems Program within NASA ARMD, and Kate will make some programmatic comments.
Thanks, Brad. 57 is NASA's first all-electric aircraft, and over the years, the team's technical achievements really serve as a pathfinder towards a means of compliance for the design, integration, and the airworthiness for electric aircraft that informs standards bodies, regulators, and industry. And that Pathfinder approach has resulted in over 100 and growing public shared publications of technical insights, lessons learned, and best practices that have really shaped industry. And this is evident by the fact that industry's electrification challenges at the time of X-57's conception are not the same challenges the community faces today that Brad alluded to earlier. The X-57's achievements have also influenced other NASA work on electric aircraft development. The array of technical challenges addressed have established a firm foundation for advanced air mobility vehicles to make progress towards the Federal Aviation Administration certification and operational readiness. Some examples are how to manage the effects of electromagnetic interference and thermal management of high-temperature electric propulsion components. Furthermore, NASA's Electrified Powertrain Flight Demonstration Project has adopted many aspects of X-57's standards development approach to their own approach to developing hybrid electric standards. So in the world of research, the true failure is not learning. So now, as a flight research program in ISP, our aim is flight, yet success is not always contingent on it. Success is rooted in the learning. So while we're maintaining the planned past X-57 closeout, which no longer includes first flight, the success and return on investment of the project has been secured through the current evidence of broadly shared learning that it's offered over the years and continue to offer throughout closeout. So what does closeout look like? Maintaining the project schedule means concluding aircraft operational activities around September of this year. And in the coming weeks, the X-57 team will be refining the scope of the technical value that can be accomplished within that target. After September, the team will focus on data analysis, paper writing, and hardware dispositioning. And the publication posting to the X-57 public-facing website is expected to grow throughout project closeout, as I mentioned previously. And the engagement by the X-57 team with standards subcommittees will also continue. While lessons learned and best practice capture has been embedded throughout the X-57 project lifecycle, several months ago the team did start the lessons learned documentation process as a formal part of initial closeout activities, and they will continue this in the months to come. In addition, we do plan to go beyond traditional programmatic closeout and host a technical interchange meeting intended to be a dialogue forum to hear and discuss X-57's overall technical knowledge capture with internal and external stakeholders. Both the team and NASA leadership is energized to continue to capture these key learnings and insights, and we're looking forward to the planned opportunities of continued engagement with stakeholders. So at this point, I'd like to offer a transition to a project perspective by handing off to Vince Schultz.
Thank you, Kate, and good day, everybody. Vincent Schultz, Deputy Project Manager. The objective of this project from the beginning was our desire to develop a test platform for these electric advanced technologies and design methods. It was never meant to be a prototype of some future electric aircraft, but again, more of a test platform. The project early on received an X-plane designation. We were very proud of that fact. It was NASA's first X-plane with a test pilot on board in many, many years. The philosophy behind X-planes is to push for major advances in aircraft technology development risk. So we are challenged to stretch the limits in a reasonable manner, a responsible manner, to get as much learning from our research that we can, all the while maintaining safety, which remains our top priority, first priority. In addition, by setting the goal of taking this aircraft to flight, we had to structure an planning with the flight rigor in mind. Higher level of research fidelity, allowing us to address challenges and identify solutions with even greater applicability to industry needs. The project recognized our learnings could truly benefit the developing domestic electric aircraft industry. One of the most effective ways to help young companies that are bringing these new technology products to the marketplace is to contribute to industry standards and to work closely with the FAA as they work directly with applicants who approach them to certify these novel technologies. Many of our NASA personnel on this project are directly involved in the industry standards groups and therefore directly contribute to the development of relevant standards, for example, standards for electric motor flight qualification or standards for distributed electric propulsion. Our X-57 team members also participate in various industry groups, for example, GAMA, the General Aviation Manufacturers Association, and freely contribute to the lessons learned discussions within these forums. We've already had several inquiries from individual companies developing electric technologies who are having specific issues with a particular technology. They approach us and ask for our help. They want guidance from us on how did we overcome similar barriers encountered. And we freely share those experiences and lessons learned as we can. So now let me turn it over to our principal investigator, Sean Clarke, and he can address some of the technical barriers we've had to overcome.
Yeah, thanks, Vince. And there's probably too much to talk about here, but I'll touch on a couple things there. As Brad mentioned earlier, this project has been going for a while. It started out as a proof of concept demonstration with a DEP wing and 18 motors on it mounted on top of a truck. And we did that to investigate the feasibility of managing all these motors in an operations and maintenance context, and to really understand this technology and how it could influence the way we design wings in the future. And it's really exciting, right? This was a grassroots experiment that came up out of a proposal from electric propulsion researchers across NASA. And it was really great to see the success of that teamwork and that research product grow into this foundational project within NASA's Aeronautics research portfolio for electric propulsion. So back then we were excited, and we still are excited about the potential for this technology. And we wanted to design the Maxwell aircraft to leverage the unique capabilities of electric propulsion components like lightweight motors and high-performance inverters and these new lithium-ion batteries that we were starting to put in aircraft. And over the course of the project, we found that a lot of those components had gaps in their technology readiness levels. So instead of just researching integrating motors onto wings, we had an extra job of closing these gaps, and this team did an exceptional job of that. We got down to the nuts and bolts of many of these technology gaps and published what we learned as we went and solved these problems. So there's a lot of great research that came out of designing this system for a flight-rated vehicle with a test pilot on board, and that was really critical to the success of this technology maturation. So it's been really impactful, and I'm excited to see how much progress the advanced air mobility industry has made along the way since this project started, and in conjunction with the contributions from this team. Some of the specific technologies that we've been working on, the battery system, we found that when we started the project, we couldn't just go get batteries off the shelf and put them in the airplane. There was no practical packaging method for these cells that safe enough to put in the seat next to our pilot. And so NASA Aeronautics and spaceflight researchers worked with ESAero and EPS, and we developed a new product that's now been commercialized. So that's really exciting for us. We did a lot of work on the inverters. The inverter system that was state-of-the-art at the time when we did our initial design back in 2015 and 2016 turned out to not be ready to fly. And all of our ground test program showed that, and we were able to go through and do a full redesign, working again across the team and make an exceptionally efficient inverter that allows us to demonstrate some really great thermal performance for the future aircraft using this technology. And then while we were doing all that, like I said, the distributed propulsion system continued development. We went through the design process for distributed propulsion motors and controllers, both software and hardware, and how all of these components fit together into a system. Went through design review cycles and have a lot of documentation and artifacts to share with stakeholders out in industry and in certification authorities. So there's a lot of exciting products there. And that's really the summary. I'm really excited to see how all these contributions will catalyze propulsion development in industry and in future research. And with that, I think I'll turn it back over to Rob.
Thank you, Sean, and thank you to the rest of our speakers. At this time, we'll take questions, and I will ask our operator to provide instructions.
The phone lines are now open for questions. If you would like to ask a question over the phone, please press star 1 and record your name. If you'd like to withdraw your question, press star 2. Thank you. The first question in the queue is from Garrett Reed with Aviation Week. Your line is open.
Hi, this is Garrett with Aviation Week. My question is, I wonder, did the X-57 program try to do too much, try to attempt too many things at once? You had several modifications planned after just the initial one, and it just seems like quite a lot that you're trying to juggle. Do you have any thoughts on that?
So Sean here, I'll give some thoughts and others can jump in too, but that turned out to be the case, I think, Garrett. The idea was to go demonstrate propulsion airframe integration and put electric motors in places on a wing that would let us design wing technology in a different way. And there were some assumptions that turned out to not be true with that. We expected that the technology that was available in the lab environment was ready to transition to the flight environment. And so we thought we could go get batteries, which at the time were already driving around in electric cars on the road, and it seemed like a small change to get them in an aircraft configuration, and same with motors and inverters. But as we dug into it, we found that we really did have to do a lot of technology development there. And that's one of the reasons we went to that staged approach that you referenced, where we went to Mod 2 was the first electric version of the flight campaign that we had planned. And that was really to retire those technology gaps and show that the new electrified components could work well before we went on to the really interesting and riskier flight tests with the high aspect ratio wing and wingtip propulsion. So yeah, we didn't plan it that way. That ended up the corner we were backed into, and we made a lot of progress toward retiring those risks, but it was a lot of scope there.
Yeah, and Brad here, that it's also important, I think, to know that unlike a company that's developing a product, when we ran into technical difficulties, we wanted to know why those difficulties existed, right? So there's a research element of that, where instead, hey, if we run into a problem with a system component, we don't just scrap it, buy a different component. We want to understand, okay, why was that not suitable? So a little bit different flavor. But I think Sean hit it. I think there was a belief that, we've been building electric motors and batteries for over 100 years. How hard could that be? So there was a belief that the technologies were more ready than they proved to be.
Thanks. And we'll take the next question.
The next question in the queue is from Rob Verger with Popular Science. Your line is open.
Hi there. Can you all hear me okay?
Yeah.
Great. Thank you so much for this update. And I wanted to ask Sean or anyone else there if they could be a little bit more specific about what the potential failure was, what the kind of tech issue behind the potential failure was that led you to conclude that a flight would be too dangerous to undertake.
We're kind of in the middle of analyzing that, so I don't have a lot of details to share today, but there was, as we got into the detailed analysis and airworthiness assessment of the motors themselves, we found that there were some potential failure modes with the motors mechanically under flight loads that we hadn't seen on the ground. And we've got a great design in progress to fix it. It's just, it would take too long for us to go through and implement that. We need to complete our design cycle, go through prototyping, and then go through component testing and system integration. And in the months left to the project, that's just a little bit too much of a delay to fit in. So we'll be going through that and closing out, and we'll see if there's any useful lessons to extract from that and share those as we go as well.
Okay, that was Sean speaking?
Yeah.
Awesome, thank you.
Okay, next question, please.
Next question is from Tom Risen with Cerium. Your line is open.
Hi, thank you. This is Tom. Congratulations on your work. I remember the thermal runaway risk seems to have been mitigated quite a lot. We don't really hear stories about lithium batteries overheating nearly as much as we did a few years ago. So I guess you are partially to thank for that. Do you think that the industry, as all these electric aircraft startups are progressing, do you think that the technology that you helped create with EPS and the SRO has significantly mitigated the risk of batteries overheating mid-flight? Do you think that's because battery packaging is still quite a priority for a lot of these companies? Do you think that it's reached an exponentially better level than when you started this project?
Yeah, and Sean here again. Thanks. That's a great question. I am super proud of the work this team did on the battery system, and I agree with you. At the time when we started the project, I don't know, my personal impression of the attitude of the industry was, we'll package these batteries and accept that they're going to fail once in a while, and you might have damage to aircraft or even more critical failure. But the X-57 team couldn't accept that. We've got NASA test pilots sitting next to these batteries, and they're sitting right behind his seat. So we went through and really pushed the team and pulled in experts from the space station battery design and really ended up with a great product with that collaboration with ESRO and EPS, like you said. EPS has gone on to commercialize that, and I think there are a couple versions beyond that. They've continued to innovate on that space, and they've got a couple product lines that have spun out of that and that the industry is using. So my impression is that this risk is greatly reduced. There's always going to be failure modes that we've got to deal with, and aircraft of the future will need to do their safety analysis, and that's part of the work we do with the certification bodies is help establish what appropriate level of reliability and safety is required to certify these products. But by demonstrating our battery system and running through cell runaway testing and showing that our battery modules survive it, industry took notice and is now using that as a baseline for safety specifications.
And a follow-up, do you think that there will be a NASA project? It seems like there's quite a lot of electric aircraft development going on in the private sector, but does NASA want to still have a similar project, do a flight test with all the tech you've got? Because you're not going to be doing a flight test, but do you think that there might be a need for one, even though the private sector is already headed that way?
I can give an opinion, and there's probably 3 other people on the line who have opinions on that too. NASA is doing lots of flight tests and lots of lab tests and lots of, CFD studies. For batteries specifically, we've got so many really smart people working across the agency on battery cell chemistry, on battery packaging, and we'll continue to publish what we're learning. One of the projects that I think Kate mentioned earlier, EPFD, is a hybrid propulsion architecture. It's using batteries as well on a couple of their platforms. Some of them are distant relatives of the X-57 design because the X-57 battery design has impacted the industry so much. So there's a lot of this technology that is going to flight test, and there are future programs at NASA Aeronautics that will be studying all of these electrified propulsion technologies as we go.
Yeah, and Brad here, if you think about what is NASA's purpose in research in aeronautics and space, it's to discover what are the barriers to modernizing the way we move people and cargo around. And electrified aircraft is not mature yet, so there are still barriers to study and to overcome. And I think so by definition, NASA will maintain a presence in working on those barriers in electric flight.
Yeah, this is Vince Schultz. I wanted to add in there that to build on Brad and Sean's points that, as I said in my opening comments, we did not set out to build an aircraft, but rather a research platform. And so in many ways, it's not that we're targeting a particular aircraft. We want to go build an industry. And so it's all those barriers, all those questions. We often get asked, with the number of companies that are advancing their technologies and advanced air mobility, why should NASA be in this space? And the answer is because we share what we learn. Everything is open, and so it really helps the industry for us to be in this space and doing the things, the activities that we've been doing and will continue to do, because it's all published and everybody can reach it.
Okay, we'll go to the next question. Also remind our reporters on the line that if they want to re-enter the queue, they can do so.
Next question in the queue is from Gina Sunseri with ABC News. Your line is open.
Yes, thank you. I know this is discouraging for you, but you will have some positive takeaways. Could you sum those up for me, please?
Yeah, I mean, I'm a fan of learning in flight tests, so I'm a little bummed out that we don't get to learn as much as we would have in flight tests, but that sure is tempered by the amazing work this team has done and published along the way. So, like Kate mentioned, we've got about 100 academic papers published through organizations like AIAA and IEEE. We've also got literally hundreds of documents that this team has written over the years in order to operate and maintain and develop these components, and we're going through those to figure out which ones are most useful for industry so that we can get them released and shared with people out there building prototype and product concepts of the future. So it's really exciting to see this research and these lessons get turned into actionable data that is out there and changing the way the market works.
Thank you.
Oh, I'm sorry. That was Sean Clarke talking.
Thank you, Sean. We'll go to the next question.
Next question is from David Curley with the Discovery Channel. Your line is open.
Thanks very much. Can you give me a sense, there are a lot of players in this area, of when you think a certified aircraft may actually fly electrically powered? And just from an emotional standpoint, I know you've said that you never plan to build an aircraft. You've got an aircraft, you're not going to fly it. How does it feel that it's never going to get off the ground? Thank you.
I don't know how to tackle the first question. Brad Flick here. It doesn't feel great to not go to flight. I think Sean used the word bummed. That is true, but that does not diminish, again, from the game-changing, really, lessons that this project team has contributed to the industry. We're in the flight test business, and we're not going to flight tests. So, of course, there's disappointment, but understandable, I think. I don't know how to... I don't know on the certification front. There's a lot of companies doing some really good stuff.
Well, a lot of folks have talked about the batteries are too heavy, that it's going to be, we need a new generation of batteries, that, that could be a decade away. I'm just trying to get some sense of timeline.
Yeah, this is Vince Schultz speaking. No, I agree. there is a lot of enthusiasm to get these vehicles to market. I know some companies are a lot closer to getting their particular vehicle to FAA certification. Hopefully, we've all seen the 60-minute special that was done, I think, last fall on one particular company getting really close. But it's a new technology, and the FAA has been approaching this cautiously, some might say, as it should. So it's difficult to predict when the first aircraft would actually receive certification, but there are certainly some that are farther along than others. I would like to add, what we'd like to think is because we're in this space and because we're developing we're trying to knock down these barriers and we're publishing the information, we'd like to think that the path to certification perhaps is now shorter because we've been in this space, that we've been able to enable, some quickening of the process for these applicants, these early entrants into this exciting new industry.
Okay, we'll go to the next question.
Next question is from Garrett Ream with Aviation Week. Your line is open.
Hi, yeah, I wonder if you might have, I know you've spoken about some very specific technical lessons learned, but I wonder if you have just more general strategic research and development, goal setting, or just like practical advice to the electric aircraft industry, because there's a lot of people, as you've mentioned, that are racing towards certifying their electric aircraft, it seems like the assumption that you can just take off-the-shelf battery components and electric motors and slap them on an airplane, that it's a lot more complicated than that, considering some of the integration challenges that you guys have had. So did you have any advice to people that are following in your footsteps when it comes to developing and certifying an aircraft?
Yeah, I could probably spend an hour on that.
Exactly.
So this is Sean again. One of the things that we talk a lot about stakeholders when we share our lessons learned, our airworthiness and certification approach. Here for a NASA airplane like we were building, we were not going through an FAA certification process. We were going through a NASA airworthiness process, which is similar, but it's designed for research aircraft. But our airworthiness approach uncovered a lot of gaps, and it gave us an opportunity to fix them in a safe way, right? We never had a failure of an electric component in flight or a failure that hurt anybody, right? We had a very careful testing program and found defects in products early on where you want to find them and fixed them, and that was very effective, but it takes some time. So we're sharing those details. We're sharing the test methods and specific challenges with different test configurations. We do environmental testing, but with these components, it was also important to do system level power testing, for example. And so all of our test plans have been described in papers and published, and we've got more documents coming out. So I'm really hopeful that's a boost for industry to see what lessons we were able to extract and how to learn them faster and cheaper. So there's a lot of things like that. Flight test is always hard. Maybe I'll turn it over to someone.
I want to build on this is Brad Flick. I want to build on Sean's last point. All of the lessons this team has learned is out there in the public domain. So our first advice to companies is, hey, go look at what's already been done, either by the NASA team or by others who have also published. It's also my other advice is to startups, stay bold, but understand that you're doing something bold. And I think it's true that you can build a machine that will fly. It is a much steeper hill to climb to make a machine that is operable and safe to operate in a general sense. So that I think is where the challenge is. Is really what are the reliability and safety requirements that it will take to get certified, and a lot of those standards are being built on what this team has done and other teams. So I would tell them to stay bold but be realistic in their goals.
And I'll just chime in. This is Kate McMurtry. That we're offering some comments here on that question, and we're also refining that perspective throughout our closeout activities that will capture not just more of the technical insights and lessons learned, but also the programmatic and the general insights. And so those, again, will be documented, captured, and shared. So stay tuned for more of those key insights moving forward.
And we will go to our next question. Just one more reminder for reporters. If you would like to get back in the queue, now would be the time to do it.
Next question is from Rob Verber with Popular Science. Your line is open.
Yeah, hello again. I'm wondering if you all had kind of more time and more money on this project, do you feel like you could get the airplane in the air safely? Or are the technical challenges so great that even with, let's say an unlimited budget and unlimited time, it wouldn't be possible to get the plane in the air safely?
I'll take that. I'll throw myself in front of that question about Brad Flick here. I think we would all say yes, if there was budget and time. Sean said now I say that with some caution. We have a design that would have overcome the current difficulties that we've had. It has not been fully analyzed and reviewed yet, but we were confident that that it could have solved this problem. Whether there were other problems out there that we haven't discovered yet is unknown. We'd like to think not, but I think we'd be confident that we could, nothing's impossible. Well, you threw it out there in the question, infinite time, infinite money. I think we can do anything with infinite time, infinite money.
Okay, thank you very much.
Bet.
Next question, please.
Next question is from Tom Risen with Cerium. Your line is open.
Yeah, thanks. I just wanted to do kind of a follow-up on that. It seems, like I said, there's been so much activity in this space since you began the X-plane project. You've really changed the game on battery packaging. That was the number one problem that these companies were worried about. I mean, I wonder even if they affected our phones, because we don't hear about that as often as we used to. So good on you for that. But I would say if there was a second big achievement you made that is really noteworthy besides battery packaging, what would that be? And you were really at the cutting edge of this, but there's been so many developments since then. Do you feel like it would be beneficial to kind of take a couple years and then revisit this, because there's been so many different changes? Like, were there a lot of changes happening in the private sector while you were doing this? Because it seems like so much has happened that maybe if you take a couple of years and come back, you might be able to revisit this in a version 2.0 or something. There's been so much happening in this space, and you were at the front of it. And what was a second big achievement you made besides battery packaging, if you had to pick one?
Well, this is Kate McMurtry. I'll take one part of that question about, implied in the comment that there's been so much happening in industry while we're doing this, and it's really that the X-57's technical challenges and the solutions behind those challenges and the open source data sharing that we've been talking about has really been an influencing factor in how the industry has been able to make other changes and tackle additional problems. And the community has really grown from it, not just in size, but in what it's been able to achieve by the influence of this project. So I think that influence can be well celebrated, and again points just to the just ongoing success of this project. So Sean had mentioned the battery packs as one of the significant developments. There's many more, but I'll hand it over to Sean to kind of echo some of what he might think boil up to another top.
Yeah, I love talking about this technology. So Sean here. I mentioned up top the inverter system. We designed an inverter with experimental components, right? Our team was out there choosing individual resistors and capacitors to make the system work. And the silicon carbide inverter technology is now airworthy, right? We took two different inverter designs. We designed a full flight-ready high-lift inverter system and our cruise inverter system at higher power, and they get more than 98% efficiency. And that sounds like, oh, good, but maybe the state of the art would have been like 94, 95% efficiency. So that's a couple percent better, but no, it's like 1/2 or 1/3 the heat that you have to deal with. And thermal problems are a huge challenge for these type of aircraft because these components run a lot cooler than the gas burning engines they replace. It's really a tricky problem to deal with the waste heat that you've got left. And the team did such an exceptional job designing a high efficiency inverter that we didn't even have cooling fans in our nacelles. And we've got papers that were just published last week that describe how the thermal performance of that system works with no fans and no cooling pumps. So it's really exciting, and I'm really looking forward to seeing that technology make its way into industry. And the whole DEP architecture, you're right, we don't see a lot of that in potential products yet in industry, but the work, the foundation that we laid there is all open source, like Brad said. We've got analysis of how the pilot interface works. The pilot's got to deal with 14 motors on this aircraft design and more on some of the other concepts that are out there. How many switches do you put in front of him so that he's not so busy that he can't also fly the airplane? That there's a lot of challenges there that this team has tackled and published. And so the whole high lift system architecture is a huge body of knowledge that has design documents and analyses and reports and papers that we're really excited to point people to and share. So maybe that's just another plug I'll give to people who are listening in. If you go to nasa.gov/X57/technical, we've got a list of those 100 papers that Kate talked about, and we'll be adding to that over the coming months as we start to put procedures and plans and test documents and other certification means and methods out there.
Yeah, this is Vince Schultz. I wanted to just add on to what Sean was saying about DEP. Although we never actually took it to flight, we nevertheless, developed an approach and showed it was possible. When we first suggested this crazy wing with 14 propellers, people thought we were crazy. But what we showed is it works, and we've got wind tunnel data, to show an approach. It's not the approach; it's not the only way to do it, but it's an approach. And it's inspired future developers. I predict you'll see more of this kind of design in the newer aircraft coming out in the years to come, inspired by what we were able to show through our wind tunnel testing and design data.
Thank you. And if anyone on the line didn't catch that URL, you can go to your search engine of choice for X-57 technical papers to find that NASA site. We'll go to the next question, and that will be our last.
Next question is from David Curley with the Discovery Channel. Your line is open.
Thanks very much. If I understand you correctly, it was the potential failure modes with the motors that led to this decision. What specifically were you worried about in those motors and their failures? And how many of the 14 motors could you lose and still fly?
So this was the Mod 2 configuration, which was the electric demonstration phase of the project. So we would have had 2 motors on board with multiple inverters and batteries to really check out that technology. The failure mode had to do with the mechanical interface between the rotor and stator on the motor and how that interfaces to the wing. And so we were finding that the flight loads were different enough, and the motor design had a couple particular failure modes that show up through our detailed analysis that show that it could seize up in flight, basically, and not be able to operate in a way that could be a safety hazard to our pilot. So like I think someone said up front, safety is our prime driver here. We want to make sure that we're developing this technology and showing a way to operate it safely. And so with the current design of the motor, without some design changes, we're not quite there. And like I said, we've got a good start on a package that would solve that. This technology is not insurmountable, but it takes time. So that was the main hurdle there. And so one thing I'll point out that just to kind of wrap up my thoughts about the the program and the technology is this technology is still really exciting. I'm really looking forward to seeing where we go in industry, and when I can put my family on vehicles that use this technology in order to do regional flights or urban flights. There's a lot of opportunity here, and I'm really proud of this team and the work they've done to help get the industry further along than we would have been. And just to be clear, the failure mode on that motor would have been for our cruise motor system, which is our very high power. It's an 80 kilowatt motor that is used for the main flight segments and would eventually have gone out to our wingtips and used on wingtip propulsion. So it's a really critical component, but not on the high lift system. And so in the high lift mode, those are not really used for propulsion. Those are used for lift augmentation. So it's also a really weird rabbit hole we could go down, but a different application for motors than for thrust.
I actually understand that. Thank you.
Yeah, thank you.
Okay, I'll just turn this back to our panel one more time. If there's anything that you'd like to say before we close for today?
Nothing. No, thank you very much.
Okay. Well, with that, I'd like to thank our speakers, Brad, Kate, Vince, and Sean, and thank everyone who joined us. We'll bring this teleconference to a close. Any members of the media looking for additional information can contact NASA's Office of Communication, and I'll ask the operator to close this out. Thank you so much.
This concludes today's call. Thank you for your participation. You may disconnect at this time.